Hello everyone! Let me walk you through the lab activity for this week. We're going to be investigating springs. We're going to use this simulation to do so, and I'll show you that in a minute. Now what we're going to do is we're going to observe its unstretched length, and then we're going to add the masses to it, and we're going to record how far it's stretched from its unstretched length, okay? So for instance, in this case, I've added 100 grams, and we see that it's stretched 36 centimeters from its unstretched length. Now 100 grams is 0.1 kilograms, so that's this point here, and 36 centimeters is 0.36 meters, so that's this point here. And then we're just going to change out this masses for a bunch of different masses, and then we're going to record how far it stretches from its unstretched length. We eventually would like to get what the spring constant of this spring is going to be, but how are we going to plot this data, and how is that going to be helpful? Well, we're going to do what we always do and start with a physics equation, and that is the force from a spring. So our spring force is equal to K, which is the spring constant, times X, which is the displacement from its unstretched length. Then when we add masses to it, how does that mass correspond to the spring force? Well, once it kind of settles down and it comes to equilibrium, the force down equals the force up. So the weight of this object will equal the spring force when it's at its new equilibrium point. So the spring force is going to equal to mg. This is our equation for weight when it's at this new point. So when we plug it into here, we're going to get that instead of spring force, we're going to get mg, and that's going to equal to kx. But how are we going to plot this? Well, we have mass data and we have x data. So we want to get only one data point on the left-hand side. So I'm going to go ahead and divide g to both sides. So the m is going to equal to k over g times x. So I just k over g is just divided g. And then I added 0 to both sides and left it off on this side just to make things a little bit simpler. And again, we're going to look at our linearization equation, y equals mx plus b. And as we see here, m is in the same position as y. So let's plot the mass on the y-axis, the vertical axis. And x is in the same position of x. So that's a little easier. Now remember, these x's are different. This stands for data in the x-axis, and this stands for the distance from its unstretched length, okay? But we're going to plot that distance from its unstretched length on the x-axis, the horizontal axis. So what's in the slope position? Well, that's going to be k over g. And then 0 is going to be our expected value for the y-intercept. So if we plot the mass on the vertical axis and the stretched length on the horizontal axis, our experimental value for k over g is the slope, and our expected value for the y-intercept is 0. So let's take a look at that. So we're going to take that data and we're going to plug it into Desmos, and we have x here is the stretched length, and m here is the mass of our object. And then we're going to be able to pull the slope and the y-intercept from this. Now we got to be careful here. The symbol for slope is m, and so is the symbol for mass. So we just got to pay attention to which m that we're using here. Well, how can I use this m to calculate the spring constant? Well, that's why we plotted it this way. So the m of the slope is going to be equal to k over g. So from our equation, we expect the slope to be equal to k over g. So m of our slope, which is the 0.29, not the mass, the 0.29 of the slope, is equal to k over g. And so we can just multiply g to both sides, and we get k equals mg. And so m here is the 0.29 from our slope, and g, of course, is 9.8. So we arrive at a spring constant of 2.84 newtons per meter. And this is how we get the spring constant from this plot. Likewise, we can analyze the y-intercept. Our y-intercept here is negative 0.00459. Now, we do expect it to be 0, but it's okay that it's not. Remember, this is an experiment, and we're also kind of measuring by hand with that little ruler. So there's going to be some uncertainty in our calculations. It's fine that this number is different than the 0 value that we expect it to be. So there's going to be 3 steps in this lab. We're going to be acquiring data in the simulation, and we're going to be measuring and determining that stretched length for the bunch of different masses. And then we're going to plot our data in Desmos. And remember, the slope is our experimental value for k over g. So we got to do that calculation to get k. And our expected value for the y-intercept is 0. And then you're going to answer questions in the lab assignment module, okay? Well, let me walk you through the simulation. So when you go to the link, it's going to bring you here. We're going to go to the far right button, the lab. We're going to click twice in order to open it up. And there's a couple things that we're going to change. The first thing we're going to do is we're going to take this damping and go all the way to the right so that it comes to equilibrium pretty quickly. We're also going to click and drag this ruler. And this is in centimeters. And we want to start by using it, finding the unstretched length. So there's no masses on here. So this is the unstretched position. We're going to take the very top of that ruler and put it right there at the top are at the very, very bottom of our spring here. We're going to pick up this mass and we're going to hang it right there from the top, wait a little bit till it comes to its equilibrium position. And now we can measure from its unstretched length to the new equilibrium position. And it looks to be right about 16 centimeters or so. So we're going to go over here to our Desmos, and we're going to be plotting that. So this first point is 0.1 kilograms. So this is 100 grams, which is 0.1 kilograms. And we measured that X position to be 16 centimeters, which is 0.16 meters. So be sure that you are converting this correctly and not putting 16, you're putting 0.16 because this needs to be in meters. And then over here, we're just going to take this and we can drag this around to different values. You can also click this to more accurately go to different points. And then you're just going to be measuring the distance from unstretched length to, remember, the very end of the spring, not to the end of the mass, the end of the spring is where our reference is, measuring what that new stretched length is going to be. You'll do that for all of these masses, and you'll fill in this table. And then I will tell you the slope and the y-intercept for this plot. From that, you'll be able to answer most of the questions in the lab activity. There's a couple more. Once you're done with that, and once you've calculated your spring constant for this spring, what you're going to do next is you're going to take this off, and you're going to add the red mass on here. And you're going to measure, wait till it comes to equilibrium. You're going to measure this length, and then you're going to calculate what that mass of this unknown mass is going to be. And you'll do the same thing for the blue one. You'll measure the stretched length and then use your spring constant to calculate or determine what the mass of this unknown blue mass is going to be. All right, let's go ahead and get started.